Hi everyone again, welcome back. So I'm just going to continue our lesson on Newton's laws. So last where we left off was going through Newton's first law, and just as a quick summary of Newton's first law, it says that more or less that if an object is maintaining a velocity, then there is no outside forces or unbalanced forces on the system, or that the sum of the forces are equal to zero. Now I just flipped it around a little bit, but it does mean the same thing. Objects in motion stay in motion, objects at rest stay at rest, unless acted upon by an outside force. So that is actually still true. But the way we use it for physics is if the object has no acceleration, then it must have constant motion, and there's no force to keep it moving. So that's the big thing. Now on to Newton's second law of motion. So Newton's second law of motion is essentially what happens to an object when there is a net force that's not zero or an outside force. And this is my favorite version of Newton's second law because what it does is it phrases as following: an object will accelerate based on how much you push it, which is a proportional relationship to the force, and how much mass it has, which is an inverse relationship. So in other words, proportion means if I double the acceleration here, if I double the force here, the acceleration will also be doubled. It's completely proportionate. But if I have, if I add a 2 to this, I actually have the acceleration. So basically what it says is if you push an object, you're going to accelerate it. And the heavier the object, the slower the acceleration, or the lighter the object, vice versa. So that tells us that. And remember, acceleration is the change of motion. So you will change the motion of an object if you apply a force. If you don't apply a net force, then you will not change the motion of an object. So it's super powerful here. So forces cause accelerations, not continuous motion, which is this line right here. Now, force is measured in a unit called a Newton. You might be familiar with the other measurement of force, which is a pound. That's the English units. But as always in physics, we're going to be using the metric unit of newtons here. The mass is going to be in kilograms, so a little different from chemistry where we use grams. In physics, we're going to use kilograms because things are a little larger in physics. And then these should be pretty familiar. These are acceleration units. Although I have it as capital A here, please note that these are the same. So the acceleration. Now the word net refers to if there's multiple forces acting on it, what's the average direction, if you will. So if you're going to have a force going up and to the right, the net force would be going on average up and to the right. So it's like a sum of the forces. So the direction, the net direction of this net force is the same direction as the net force here. So these are related. So I know that might have been a little confusing, but I'm going to go into more detail on this in later slides. So this is just another version of the same thing, but F equals ma. It's the second most famous equation according to physics, along with E equals mc squared. It means the same thing. But I'm going to be teaching you how to use the net force here and how to model the motion right here. So the right side of this equation is what is the object doing? What is its motion? And this models what the situation is. So if we model the situation to the motion, we can describe what's happening and make predictions, solve for acceleration, solve for forces, all that fun stuff. And of course, this is just another way to rewrite it. If I have time, I'll demonstrate this property, but I can find the mass of my car without weighing it, which is pretty crazy, right? So the way you can do that is if I put a scale right here, so this is something I really do, I could put a scale on the car, and I could push it. Now I'm not lifting the car, so it's not heavy in terms of, I'm lifting the mass of the car. I'm just overcoming the inertia of the object, so I'm just pushing it. It takes like 100 pounds. Anybody could do it. It's not super hard, but it's not impossible. And then I can measure the acceleration simply by measuring how far it went and how long it took. So I could do d equals 1/2 at squared, so assuming the car starts at rest, which it does. And with the force and the d equals 1/2 at squared equation, I can solve for the mass of a car. So I do this as another demonstration to show you how we know the mass of the sun, right? That's crazy. You can't like just take it and weigh it, right? We don't look or weigh it. We look at its motion. So we know the acceleration of the sun in the sky and, in a certain perspective, and we can measure something like the gravitational force. We could measure the mass. It's pretty amazing. Pretty cool, right? You can measure things without actually weighing them. So a big proponent of this next unit is about identifying forces. So, and be able to predict their motion. Now, right now, these are just some random examples that have values here. But I want to show you the value of identifying the direction and the value of the force to show you how you can predict motion, right? If you look right here, I could see I have a rightward force of 5 newtons and a leftward force of 3 newtons. I don't need physics to kind of look at this, but this is bigger, 5 is bigger than 3, so it's probably going to move forward in the right direction. Not in the left because there's not enough force. So that's kind of the idea here. If you look here, I only have one force moving to the left, so this object's probably accelerating to the left. And vice versa, if you look at situation C, I see the up and the down force are actually the same, which means they're going to cancel. So if I have a balanced force system, that object's going to maintain its motion. So there you go. That's how if we identify these forces and kind of read into their value and their direction, we can know what the object's doing. And then this one, the upward force is bigger than the downward force, so this thing is moving up. Actually, it's accelerating up because the forces are not balanced. So that's how we apply Newton's first 2 laws. There's a ton of forces. I actually left the reading in the slides for you for later, but I'll introduce them very quickly. So the frictional force is the force that opposes motion, and it is in contact with things. So this could be like a crate on the ground, or it could be, for example, air resistance, although I have it actually as air resistance. But anything that causes, or I should say, it's the direction of the force that opposes the motion. So if the object's moving to the left, this is my left, sorry, it's going to oppose that by going opposite to the right. Tension is the type of force for strings and chains and whatnot. So anytime something's being hung by, here's an example right here. You could see my keys right here. This would feel a tension right here because it's being pulled actually by my hand and down by gravity. So a pull apart is actually a tension. The normal force comes from any surface pushing against it. So anything that has a surface will have a normal force. So if I push on the table right now, I know you can't see it. There's a normal force going up against the table. If I were to push against the ceiling, the normal force would be pushing down against me because the ceiling can only push straight down. If this were a wall, the normal force would be where my fingers are, so away from the wall. Applied force is just a given name for a push. It's just like you push something, you apply a force. And spring force has to do with springs. Now these all need contact, which essentially means that the objects have to be physically touching one another, which is different than these action at a distance forces, which is just a big way for field forces. So for example, I know I don't need the earth to physically touch this for gravity to act on this. That's what it means to be at a distance. So we have the gravitational force and the electric force. We won't do electric force until after, second semester. And the magnetic force we won't even talk about, at least in this course. Unless it's unless they're doing college course, then yes, we'll cover this. But in the high school course, we won't cover this. So you're going to have to learn how to identify all the forces acting on the system. So this is just a very quick example, but there is a surface, surface force. They call it surface, but there's a normal force here, and then there's a gravity and electric force here. So being able to look at a situation and identifying forces is very important and a big skill. We're going to be doing this for the next couple of classes, so I'll be modeling identifying forces as we go through. Like I said, these are all the descriptions of the forces. I'm not going to read them right now, but they're for you for later. But I do have to talk about really briefly a calculation of the object's weight or gravitational force. So we can find an object's gravitational force if we know the gravitational, the acceleration due to gravity, which is that constant 9.81 meters per second squared. So F equals ma, right? So force is equal to mass times acceleration. But in this case, if we know that this is g, then we're going to be very specific to the force due to gravity. So we can calculate an object's weight, and the symbol is Fg for the force of gravity. So I'm using the word weight, but it's synonymous and can be used interchangeably with the force of gravity. And actually what I'm going to do is give you one way to calculate the force of gravity here, and then I'm going to give you another way. So there's actually multiple ways to calculate the force of gravity. And this is just more details and exactly what I just described right here. So F equals ma, weight is mass times a, in this case specifically g. So all objects accelerate at the same rate. So the thing that changes the weight of an object is an object's mass. Now weight is measured in newtons and mass is measured in kilograms. So when you measure yourself on a scale, you're measuring your weight. So 100 pounds is your weight. It's the push down onto the scale, because the way the scale works, it records how much it has to push back up on you. So it's a force measurement. If I want to measure your mass, we don't need gravity, we just see your ability to change motion. There's actually a device called a inertial balance that measures mass only by shaking an object like this. You see me shaking in the video. Now the reason why it measures mass is because it doesn't, if I shake horizontally like this, then I'm not using gravity. I mean, obviously it's acting this way in terms of gravity, but to change the motion is in the same line, so I'm not changing the height of the object, therefore not changing the gravitational pull on the object. So anyway, point being that this is weight, not mass. In fact, here's a quick example for you. If I wanted to calculate my weight on Earth, my weight would be the 75 kilograms times g, 9.81. So for someone that's like 120, actually this is a little larger than 120, let's make up a number, like 200 pounds, that's not right, but weighs about 700 newtons. So that's actually a pretty, relatively reasonable amount for a person on Earth. But what happens is, if I go to the moon, for example, and I put that person on the moon, their mass is the same. So in other words, they are made up of the same amount of stuff, unless this person lost a leg or has grown an appendage. Really unlikely. But also the point being is their mass doesn't change. The way they're made up remains constant. That's mass. But you might hear that you weigh less on the moon, which is true. G on the moon is 1.6, so it's 1/6 less than that of Earth. So you weigh way less on the moon. So here is, someone weighing 700 newtons, someone weighing, 120 newtons. So if you want to lose weight, you could be that person, and you could say, go to the moon, because that's a great way to lose weight. But I think what you really want to lose is mass, because mass is the effective amount of how much you're made out of. So that's different. So just some fun things right here. So something that weighs about 110 pounds will weigh about 490 newtons on Earth. 81 newtons or 18 pounds. Look at that. That's crazy, right? So Jupiter, we use G as 29. You weigh 330 pounds. So that's your force down due to gravity. Crazy thing about this is you look the same. I would look like this, and I would weigh 330 pounds, or however much I weigh. I don't weigh 110. Just throwing that out there. But this right here, if you look at the acceleration due to gravity on the sun, you'll see that it's 274 meters per second squared. So if we do the calculation now, it puts you at 3,000 pounds. So again, you would look the same, but you would weigh as much as a car, actually more than a car. You would feel pressure. So imagine that on the sun, you wouldn't be able to like literally lift up your limbs or anything. I mean, even as 300 pounds, that's pretty tough too. Assuming, of course, there's a surface and you can actually do this, but, you know, hypothetically here. So this is a brief review on mass and weight. Mass is the inertia of an object, how much stuff it is, and its resistance to changing motion. But an object's weight is how much force gravity pulls. It changes with surroundings, I mean with different planets, because G is different on different planets, measured in newtons. So a fun fact, quarter pounder is 1 Newton. So if you want to get a sense of how much 1 Newton weighs, go get a quarter pounder at McDonald's. These are more forces just to look at. So let's continue here. So we're going to focus, of course, on the net force of systems. Because typically, and you already saw an example, we have more than one force acting on our system. So we need to be able to analyze that. But also, what happens when you have different directions, right? Up and down and then to the right, or in this case, up and to the right. Like, how do you add up all those forces? The way we're going to do that is we're going to add forces together in their own direction. And kind of similar to finding the velocity vectors, which we did in projectile motion, we're going to be finding the force vectors here in x and y using trig, summing those up, and then combining them in the end to make a triangle. So I know I kind of explained that pretty vaguely at the moment, but we have to take into account direction. We can't just find the magnitude of these net forces. We need to know not only which way up and down, but which way left and right. Now, we have a special name in physics for drawing the forces in objects. It's called the free body diagram, FBD. So that's what this is right here. And it exactly does what I said. It models the forces acting on the object. Not by the object, but on the object. So it's what this is feeling versus what it's doing. So we'll go through, again, this is something we'll model several times in the next couple of weeks. Some general rules, I'm going to go through these pretty quickly here. So FBD is free body diagram. We're going to put all the forces on the object as shown right here. And specifically, single object, which means that only one object at a time. So there are times when you have two objects. They each get their own free body diagram if that is the case. Sorry about that. So we need to know the name of the forces. So this sounds obvious, but definitely need to make it a point here. You need to label the forces because we need to know what they're doing. As equally important, you have to draw them in terms of their relative sizes. So if it's a big force, it should be a big arrow. If it's a small force, it will be a small arrow. Definitely need to do this to model the situation correctly. I usually draw them as boxes, although you can draw objects, that's totally fine. And I usually take the force and I put it right in the middle of the object. Even though, you know, for example, friction might actually be acting on the floor here, I move it up to here just so I get a better sense of what's going on. It's actually easier to read a force diagram with all of them starting in the same spot. So only put forces acting on the object. And also only forces. Obviously, you don't see anything like acceleration or velocity or displacement. Now, you may absolutely use it to model the question in terms of drawing it, but not on the diagram. Especially for AP classes, if you are asked to draw a free body diagram, it must be forces only. And only the forces, not their component forces. So not force, you know, for example, if you look at FF right here, force of friction, you'll see that it actually has an X component and Y component. Now notice that this doesn't include that. It just wants the total force right here. So I kind of went through these already, but what a net force is, it models the sum of the forces. So it's kind of like an average of what's going on. So if I have two forces to the right of 5 newtons, it's like one force of 10 newtons. If I have forces equal and opposite, they're going to cancel. And if one's bigger than the other, the bigger one wins. and the value at which it wins is the difference between the two. So you can see like that. Now, I just explained this logically right here, but what we're going to do is kind of analyze these in more detail. So I'm actually going to skip that and go right to the point of this. So, modeling net force, when you have forces that are not perfectly in one direction, you have to model them by their component forms. So, although situations are always different, I'm going to go through the following steps. So, here's an example question, both in lab if you're doing lab with me, or doing your homework. So if you can see force A, B, and C here, notice that there are all sorts of different magnitudes and different directions here. The question is, what is the net force? So what this is really asking is if I can lump these into one force, how would it act? That's the net force. How we do such a thing is the following. We will draw a free body diagram if it's not already there. We must break apart each force into their x, y components. So we're going to use trig to do that. So we're going to find cx and cy, ay, ax and ay, and by and bx. So we're going to describe the forces in x and y for this side of the equation. So what is the net force? Then we're going to add up all of the contributing x forces and add up all the contributing y forces as separate calculations. And then I'm going to redraw the combined forces of x and y and make make a triangle from that, because to add an x component and a y component, what we're really doing is finding the hypotenuse of that triangle. So by summing up all these forces and finding their x and y's and redrawing the triangle, we're essentially finding the net force on the situation. And we're going to solve for the hypotenuse of that new triangle. Now, you're probably like, oh my goodness, you just said all this stuff. So in the next video, I'll model this specifically. I'm not going to specifically, say all this as I do it, but this is the process. This is how I'm thinking as I do a net force problem. So in the next video, I'll do that.